All right, so the plan for today is just to wrap up the last couple of questions from last time on quadratic equations, and then move on to chapter 8 on rational expressions and equations. So rational expressions is kind of a something like a capstone topic in the course. It combines together a lot of the topics that we've talked about before in the course. Particularly, we're going to be using factoring quadratics a decent bit in chapter 8. So this will also serve as some extra practice on factoring as we go through chapter 8. A couple administrative details. Unit 2 exam is scheduled for this week. It is available on WebAssign and Examity. I sent out an announcement yesterday about exam 2. It's due Tuesday, a week from today at 11:59 p.m. And as I've said several times before, don't wait until the last minute or the last day to complete the exam, just in case you have a technical problem or something comes up. Give yourself a little bit of margin there. And the quote of the day today deals with margin, and we've talked about this once before in class. Sorry, now that spring has sprung, my allergies have also sprung. I usually have a week or so around spring and a week or so around fall where no amount of Allegra seems to do very much. But anyway, so we had a quote earlier in the semester about margin, and as we approach final exam time, and when you'll have projects and presentations and all kinds of things coming up around the same time, as well as the Unit 2 exam this coming week, the idea of margin, I think, becomes more important. So the quote for today is, "You must create more margin so you have room for what's important, not merely urgent." And as I kind of mentioned before, that often when you build margin into your schedule or into your life, catastrophes become inconveniences, and when you lack margin, inconveniences become catastrophes, right? So the internet going down for a few hours is an inconvenience most of the time, but if you've waited until literally the last minute to, say, complete an exam or to turn in a project, the internet going down for a few hours is a catastrophe. So when you build in margin, and this is something I see in my life all the time, if I leave a few minutes early, I'm less frustrated, less annoyed on the road, less likely to make a bad decision. I think the same thing applies in many areas of life. So as we go into finals week, if you can say no to, say, maybe one social get together or something like that you would rather go to, and instead maybe get that paper done or get that outline turned in or something, and kind of get ahead of the work instead of constantly being back on your heels, that's a very good feeling to have. I'm not saying that I always do that. Sometimes I do, sometimes I don't, but I'm much happier and much less stressed when I am able to do that. Okay, and then just a reminder, our last few class days, this is what they look like. Again, just wrapping up chapter 8 and the material for the course. We'll have an optional review session on the 9th from 8:30 to 10, or 8:30 to 10:10. Our same class time as usual. This is during final exam week. So I'm kind of fudging the numbers a little bit here, because we would normally, our final exam would normally be scheduled for Thursday. But given that the final exam, sorry, our final exam time slot would normally be on Thursday. So it would, our time slot for something like a review session kind of ought to be Thursday, but given that Thursday is so late in the exam window for the final exam week, the final exam will be on WebAssign using Examity, same setup as the unit exams. Given that Thursday would be so late in this window, I think it makes more sense for us to just meet kind of like or have the availability to meet kind of like a regular class meeting on Tuesday. If you have any questions, I'm happy to answer them. I'm basically going to just handle this like in office hours. So if you have questions, pop in. If there's only one or two students, I'll basically treat it like office hours. If there's more than one or two, then we'll kind of, pick popular topics that people are asking about and then treat it a little more like a class session. So that's optional. It's not an official class session on the 9th, but we're just required to, if we do a virtual exam like we're doing, we're required to do something during that final exam time slot. And I think this is the most sensible alternative rather than using the Thursday time slot when the exam would be due that next day. And as just like the Unit 2 exam, don't wait until the last day or the last minute to complete the exam. Maybe I should also just paste that down there for future reference. Okay, so I think that that handles the administrative details for the day. Give me 1 second here. I'll be right back. Okay, so again, in 7-6 quadratic equations, wrapping up chapter 7 on factoring. We solved many examples last time, both in lecture and on the worksheet. But just recall the strategy that if we have A times B equals 0, then A equals 0 or B equals 0. We call this the zero product property. If we have a product of two things equaling 0, at least one of the two things has to be 0. So if I have a linear equation, remember the strategy was something like isolate the variable term, isolate the variable, and simplify. If I have a quadratic equation, unfortunately, I have two unlike variable terms. So if I tried to get all the variable terms on one side, this 3x squared and this 26x can't combine to make a single term. I kind of get stuck, right? If I try to go down that same path that I used to solve linear equations, I immediately hit a roadblock. I don't know how to deal with the different terms, the x squared and the x term. So we have a different approach. We want to get a quadratic equal to 0 and then factor it. Maybe if I have something like x minus 3 times x plus 4 equals 0, if I can get to this point somehow, then I can apply my zero product property. I have the product of two things multiplied together equaling 0. Well, that says x, well, one more step, x minus 3 equals 0 or x plus 4 equals 0, which says x equals 3 or x equals -4. So a couple of things we saw that were different than solving linear equations. One is that we seem to often get exactly two solutions. That was something that didn't happen in linear equations. In quadratic equations, we can get most of the time we get two solutions. We can get one solution. I don't think we've seen a case of that yet, but we may in the future. We can get, I suppose we could get 0 solutions, something like x squared plus 1 equals 0. And I suppose we could also get infinitely many solutions if we had like x squared equals x squared or something like that. So if we think back to our linear equations, we could get 0, 1, or infinitely many solutions. And with quadratic equations, we could still kind of get 0, 1, or infinitely many solutions, but kind of the standard case is for us to get two solutions, as opposed to the linear case where kind of the standard case was to get one solution. So we still have those kind of edge cases, those interesting, strange cases still occur in quadratic equations, but our kind of, standard case is to get two solutions as opposed to linear equations, one solution. Okay, so this use of the zero product property is predicated on having a 0 on the right-hand side. So the first thing that we always do is get everything on one side. And of course, I mean, I could move everything to the right side or move everything to the left side. Here, I'll move the 26x to the left side. And now I have a quadratic expression equals 0. My goal is to factor and then use the zero product property. So this looks like a fairly complicated one to factor. So I see that A is 3 and C is 48. Let me, right over here, A times C is 3 times 48. And 48 has a lot of factors, so I think I'm going to go the extra step here and factor this all out into prime numbers. Well, 48 is 2 times 24. And 24 is, let's say 6 times 4. 6 is 2 times 3. 4 is 2 times 2. So now I'm looking for two numbers, m and n, that multiply to make 48, and then add to make this cross term here, this middle term, add to make 26. Remember, the idea is that we want to figure out how to break up that middle term into the sum of two terms so that we can then use factoring by grouping. Need a little more room here. Okay, so of course we can have m is 1, and then n is going to be 3 times 48. Is that sum going to be 26? No, so I don't really care what 3 times 48 is. M can be 2. We have a factor of 2 present up here. So 48 is 2 times 24. 24 times 3, I think, is 72. That sum is not 26. M could be 3 times 48, also not 26. M could be 4, 2 times 2. This would leave me with 3 squared times 2 squared, or 9 times 4, or 36. 36 and 4 is also not 26. M can't be 5. We don't see a 5 in the prime factorization. It could be 6. 3 times 2. It would be 6 times what? 24. That almost works, but not quite. We're seemingly getting close, though. 7 doesn't work. 7 is a prime number, but it doesn't occur in the prime factorization of AC. 8 is 2 cubed. So like 2 of these 2's and 1 of these, leave me with 3 squared times 2. 9 times 2 is 18. And we do see that 18 plus 8 does give us 26. So I'm going to factor 26, or sorry, I want to split 26x up into 18x plus 8x, or 8x plus 18x. It doesn't matter which way. And then I want to factor by grouping. So now I'm going to look at these first two terms. Is there anything I can factor out? Is there a greatest common factor? Well, nothing really other than an x. And then I look at these last two terms. Well, there's no x to factor out there. But I do notice that these are even numbers, 18 and 48. So I could factor out a 2 definitely, but I could even get a little more than that. I could actually factor out 2 times 3, or 6. 6 times 3 is 18. And 6 times 8 is 48. And I knew that this was what I was going for, 3x plus 8 left over. So that also gave me a little bit of a hint as to what I wanted to factor out. And now I have a common factor of 3x plus 8 in each of these two bigger terms. I can factor that out. Okay, and now I can apply my zero product property. I can say either 3x plus 8 equals 0, or x plus 6 equals 0. This gives me the solution x equals -6. 3x plus 8 equals 0. We could take a couple of steps here to solve it, no problem with that, but this will end up being x equals -8 over 3. These are my two solutions. X equals -8/3 and x equals -6. Both of those numbers, if I substitute into this original equation, will give me a correct equation. And I think we'll actually just take this problem and move it over to the worksheet side of things, just to get a little extra practice. There we go. Okay, so maybe if you want to take, let's actually take about, let's take about 6 minutes for these first two problems. And then we'll touch base after 6 minutes, and then we'll take a few more minutes for this third one. So take about 6 minutes for these first two. And then if you get done before 6 minutes, you can start working on the third one. If it takes you longer than 6 minutes, again, I'm not, coming up with these times very precisely. I'm just making an educated guess here. So we'll take about 6 minutes for these first two, come back and discuss them, and then take a few more minutes for the third one, come back and discuss it, and then take any questions in general about chapter 7. All right, so in about 6 minutes, we'll discuss the first two. Okay, it's been about 6 minutes. So looking at the first problem, again, we get all of our terms on the left-hand side. So we get 8x squared plus 25x plus 3 equals 0. And then we use our AC grouping method. We say a times c equals 8 times 3, or 24. I'm looking for two numbers that multiply to 24 and that add to 25. 25 being the middle term, 25x, the coefficient of the middle term. And my actually first one in the list works. So when m is 1, n is 24, and 1 plus 24 is 25. So sometimes this can be an easy one to forget, even though it's the simplest one. We might start jumping into factors like 2 or 3 that we see in the prime factorization of 24, but we never want to forget that 1 is always a factor as well. So I made this 8x squared plus x plus 24x plus 3. Again, if you made it 8x squared plus 24x plus x plus 3, you would get the same final result with just a slightly different intermediate step. But we see from the first two terms, 8x squared plus x, we can factor an x out, and we're left with an 8x plus 1. And from our last two terms, 24x plus 3, we can factor a 3 out, also left with 8x plus 1. And we can then factor that common factor of 8x plus 1 out, and we're left with x plus 3. So we get 8x plus 1 times x plus 3 equals 0. Product of two things is 0, so either the first thing is 0 or the second is 0. Either 8x plus 1 equals 0 or x plus 3 equals 0. And solving those two equations gives me x equals -1/8 or x equals -3 as my two solutions. For the second problem down here, again, we start by moving everything to one side. I'll choose to move everything to the left side because 6x squared minus 2x squared gives me a positive number for a. I would usually rather have a positive number for my leading coefficient, for the coefficient of the x squared. Just kind of makes things a little easier to deal with. So I move everything to the left by subtracting 2x squared and adding 7. This leaves me with 4x squared minus 20x plus 25 equals 0. And just like before, I do my AC grouping method. A times c is 4 times 25, or 100. I'm looking for two numbers that multiply to 100 and that add to -20. And I could start going out, 1 times 100, 2 times 50, and so on. But when you start getting used to this, you might be able to just look at this and say, okay, what are two numbers that multiply to 100 and then add to -20? Maybe -10 and -10. And yeah, that seems to work. -10 times -10 is positive 100. -10 plus -10 is -20. So the more that you get used to this, the less you have to start writing out the entire list. You can kind of check as you're going along the list, or even just jump to the middle of the list if you can recognize a certain pattern. But I do see -10 and -10, so I want this -20x to become a -10x minus 10x. And I can factor a 2x out of my first two terms. That leaves me with the 2x minus 5. And what comes out of the next two terms? I guess I could factor a 5 out of there, but I want to end up with a 2x minus 5 left over. So I probably want a minus 5 to come out so that my signs work out correctly. And now I factor 2x minus 5. And I actually see, interestingly enough here, that I get the product of two things equals 0, but it's actually the same thing. It's actually a perfect square. I might have also recognized at this point, I might have happened to recognize this as a special product, as a perfect square. I would see that it's a candidate for such a special product because the constant term and the quadratic term are both perfect squares. The quadratic term is 2x all squared, and the constant term is 5 squared. And then the question is, does the middle term look like 2ab? Or 2 times 2x times 5, and it does. It's minus 2ab. So I might have recognized the special product, or if I didn't recognize that, I can always just do the AC grouping method and I still get the answer that way. So either way is fine. But I see, kind of strictly speaking, if I wanted to go from here, I would be writing a statement something like 2x minus 5 equals 0, or 2x minus 5 equals 0. But that's obviously the same answer, right? So I just see that I get one solution here. 2x minus 5 squared equals 0. Well, if a number squared is 0, the only way a number squared can be 0 is if the number itself is 0. And 2x minus 5 equals 0. I add 5, I divide by 2. My one and only solution to this quadratic equation is x equals 5 halves. So this is one of those edge cases that I was talking about, where in quadratic equations, we can get a single solution. The usual case is for us to get two solutions, but there is an edge case where we have a perfect square quadratic, and we do end up getting a single solution because this factorization that we want to apply the zero product property to really just has the same factor repeated twice. So we don't get two distinct solutions from these two equations. We just get a single solution. Okay, and then take a look at this last problem. Let's take about 3 minutes for this problem, and then we'll come back and discuss. So take about 3 minutes, be back in a few minutes. Okay, it's about 3 minutes. So working through this one, if we start by getting everything on one side, I'm going to choose to get the stuff from the right side to move that to the left side. Even though it's moving more terms over, that will keep my coefficient of x squared positive. So when I move everything over, I see that I get 4x squared minus 9x minus 5 on the left-hand side equals 0. And then maybe this is one where I would try to factor by guessing. And I'm kind of getting close, right? If I could have a 2x and a 2x, and then I need a 5 and a 1 to multiply to make the minus 5. One of them has to be negative. If I do the minus 5x, or the minus 5 and the plus 1, I have minus 10x, and then plus 2x is negative 8x. Well, that's the wrong cross term. And if I did it the other way, of course, I would just get positive 8x, so that doesn't really help. That's not a plus, that's an arrow. If I tried to factor the other way with 4x times x as my firsts, well, then I could put the 5 in the same parentheses as the 4x and the 1 in the other one. And this, again, almost works. I need to have opposite signs, though, to make a minus 5. So this gives me, for a cross term, a minus 5x plus 4x that's minus x. If I change the signs, that's just going to give me a plus x. That's not going to really fundamentally help. So could I put a 5 here and a 1 there? Well, that doesn't really help either, because that's going to give me a 20 against the 1. There's no way I'm going to make a 9 out of that. So if I look at 4x squared minus 9x minus 5, using something like a guess and check method, it seems like I'm not going to be able to factor this. Let's double check that using AC grouping. AC would be 4 times negative 5 or negative 20. So I could have 1 times 20, 2 times 10, 3 doesn't work, 4 times 5, and that's about it. They need to have opposite signs. And we need m plus n equals negative 7. Did I? Yeah, I copied this down. I copied down one line incorrect, that this should be negative 7. Somehow I got a 9 there, but it should be negative 7. But either way, I do see that with opposite signs, do I have a difference of 7 between m and n anywhere? No, I don't. This isn't going to work. That's not going to work. That's not going to work. So this is prime. Unfortunately, it doesn't factor nicely. So if I look at this equation, I can't find solutions to it. That means I can't find solutions to this equation, at least not using factoring in the zero product property. So I'm going to put kind of in quotes, no solution, but with the important kind of caveat, using factoring and zero product property. So this isn't to say that we might not be able to find a solution another way, but it's saying we can't find a solution using factoring in the zero product property. So this is something kind of interesting that comes up also, that in linear equations, we were always able to find a solution. I mean, well, let me say, we were always able to get an answer, right? Sometimes the answer was there's no solution to this equation. It's a degenerate equation. Sometimes there were infinitely many solutions. Sometimes there was exactly one solution we could find, but the same procedure always gave us an answer. But here we're saying, well, we have kind of an answer. We searched for an answer using factoring in the zero product property. We searched for a set of solutions using this method, and this method didn't work. But that doesn't necessarily mean there's no solution to the equation. There might be a value we could plug in for x, like maybe the square root of 2 or something, that ends up working, but we just aren't able to find it using this method. There is going to be another method in MAT090 that you'll see where it will be more general, kind of like the linear equations method, where you'll be able to find all the solutions. So there will be a method like that, but just not in MAT090. Okay, so we saw a couple of kind of strange cases, as well as one that was a little more standard up here. Are there any questions on chapter 7, on factoring, on quadratic equations, anything like that? All right, so then moving on to rational expressions, chapter 8, and the first section, simplifying rational expressions. So what is a rational expression? Well, a rational expression is simply a polynomial divided by a polynomial. So this could be something really as simple as even something like x over 3, or we might even, if we really wanted to be pedantic, we could even say a fraction that's like 1/2 is a rational expression because constants are polynomials. Something like x over 3 could be a rational expression, but usually when we think of a rational expression, if we're really trying to be in the ballpark of rational expressions and using the techniques and the tools that we're going to be talking about in chapter 8, usually we're thinking that there's a variable in the denominator. So while these might, technically satisfy some definition, usually what we're thinking of is something like maybe 1 over x, something like maybe 3 over x minus 1, something maybe like x plus 1 over x squared minus 4. We could have, say a cubic over a 5th power polynomial. And I ran out of room. We could leave it like that. That's fine. So these are really what I'm kind of generally thinking about when I talk about a rational expression. Right. So the tools and techniques we're going to develop here are really going to be geared toward handling situations where we have variables in the denominator. So we could have a monomial in the denominator, we could have a binomial, we could have a quadratic, we could have a higher order polynomial, but these would all be rational expressions. Now, one thing that we might realize is once we start putting variables in the denominator, we kind of have an issue that pops up. We have, for 1 over x, I can't plug in x equals 0. Otherwise, I would be dividing by 0. And we know that that's like one of the big things that's not allowed in math. Right? Dividing by 0 in math would be like telling a physicist that you're going to work their problems without conservation of energy or something. It's like, so as soon as we start putting a variable in the denominator, when we just had a linear expression or a quadratic expression, we could plug in any value for x we wanted. Right? If I look at, say, this quadratic expression just by itself, I could plug in x equals 0 or x equals 1 or x equals 1,000 or -20. There's no restricted values. There's no x's that I can't plug in to this 3x squared plus 26x plus 48. But if I look at something like 1 over x, I can't plug in x equals 0. I can plug in 2 just fine or -5 just fine, but not 0. Similarly, like 3 over x minus 1, I can't plug in 1. I can't actually plug in 0 here because an input of 0 gives me a -1 in the denominator. And as long as the denominator itself is not 0, then I'm fine. So it's not really so much what the input is, it's what the denominator ends up being for a certain input. Or if I see that I have a denominator x squared minus 4, well, x can't be 2, but it also can't be -2. Either one of those inputs would give me a 0 in the denominator. Any other x is fine. If I have x equals 10, 100 minus 4 is 96, I can have a 96 in the denominator, no problem there. Note that really the only problem that comes up is 0 in the denominator. I really don't care for the purpose of looking at these restricted values. I really don't care what the numerator is doing. The numerator is not going to break anything. The numerator is just a polynomial. I can evaluate a polynomial at any number, no problem there. It's just the denominator that can cause some problems. Or something like this, who knows what all the restricted values are for this. We can certainly see that x equals 0 is going to be 1, but then we're going to get something very messy if we try to find any others. But so x can't be 0, and probably some other values as well that it can't be. But we can see clearly that if we plug in x equals 0, we get 0 on the bottom. So that's the first thing we're going to look at here. We're going to go through just a couple examples, and we're going to determine the values for which the rational expression is undefined, also sometimes called restricted values. And really all that we're looking at here is when is the denominator 0? So when is 4x equal to 0? Well, this is just a linear equation in one variable. We just divide by 4. So my restricted value is x equals 0. So in other words, I can plug any value of x into this rational expression with no problem, except x equals 0. Similar question, slightly more involved details. 3x minus 1 over x squared minus 1. What is the restricted value or restricted values? Well, again, I look at when is my denominator equal to 0. Well, x squared minus 1 equals 0. That's a quadratic equation. I notice that it's a special product, x minus 1, x plus 1. It's a difference of two squares. So x minus 1 times x plus 1 equals 0. The product of two things equals 0 means that x minus 1 equals 0 or x plus 1 equal to 0. And I see that I have restricted values of plus or minus 1. I can't plug in x equals 1 into my rational expression. I would divide by 0. But I also can't plug in x equals minus 1. So I might indicate that something like this. X cannot be equal to minus 1 or plus 1. Okay, let's jump over to the worksheet. And I have 3 problems here. Again, these problems will also get us a little bit of a reminder, some practice on linear equations, but also quadratic equations. So let's take about 4 minutes or so to work through these 3 problems. For each of these 3 rational expressions, what are its restricted values? What are the values of x that cannot be plugged in that would lead to a 0 in the denominator? So take about, what did I say? I think I said 4 minutes. We'll take about 4 minutes, go through these, and then come back and discuss them. Okay, it's been about 4 minutes. We see for the first problem, we're looking for when 3x minus 1 of the denominator equals 0. That's going to give us the inputs that we can't plug in that would yield a 0 in the denominator and cause a problem. We add 1 to both sides. We get 3x equals 1. So that isolates the variable term. And then we isolate the variable by dividing by 3, x equals 1/3. So we see that we cannot plug in x equals 1/3 into this rational expression. Otherwise, we divide by 0. For the second problem, we have, again, similar setup, similar qualitative idea. When is the denominator 0? But here we have a quadratic equation. So the equation solving steps are different. We're looking for when x squared plus 3x plus 2 equals 0. Well, that left side factors into x plus 1 times x plus 2. We have the product of two things equals 0. We know that either the first has to be 0, x plus 1 equals 0, or the second, x plus 2 has to be 0, which means x equals -1 or x equals -2. And remember, what we're solving for here are the restricted values, the problem inputs that give us 0 in the denominator. So we cannot plug in -1 or -2 into this rational expression. And then lastly, we have this third problem, x squared minus 3x plus 28 in the denominator. So when is that 0? Again, I have a quadratic equation. I'm looking to factor the left-hand side to get a product of two things equals 0, use my zero product property. I see that this is a quadratic equation where the coefficient of x squared is 1. And my strategy there was, well, either guess and check like I did up here, because this was a pretty straightforward one, or to use the m and n breakdown again, but I'm looking for two numbers that multiply to the constant term, 28, and that add to -3, the coefficient of the middle term. So similar in nature to the AC grouping method, but my goal would be to factor this as x plus m times x plus n. And if I look at the factors of 28, I have, well, 1 times 28, 2 times 14, 3 doesn't go into 28, 4 times 7, 5, 6 don't work, and then I'm back to 7 times 4. That's a repeat. The product has to be positive 28. So they have to have the same sign, both positive or both negative. So they would have to both be negative to make a sum of -3. But I don't see any choice for m and n whose negatives add to -3. So at this point, I would basically have to say, under the techniques that we currently know in MAT090, we don't find any restricted values. Now, it's kind of important to note that that doesn't mean there are no restricted values. There could be restricted values, but that we would need another technique for MAT108 to determine what they are. Now, to build off of this example, what if I had instead had, instead of a plus 28 here, if I had a minus 28? Pretty minor change. What does that change? I have a minus 28 here, so I'm looking for two numbers that multiply to -28 and still that add to -3. But now the product being negative means my m and n will have opposite signs. They'll still be the same base numbers, 1 and 28, 2 and 14, 4 and 7. But now I'm looking for opposite signs. I'm asking, do any of these have a difference of 3? And if I do -7 plus 4, I think those are two numbers that multiply to -28 and then add to -3. So I should now be able to factor this into x plus 4, x minus 7 equals 0. If we double check, that will work. And this gives me x plus 4 equals 0, which means x equals -4, or x minus 7 equals 0, which means x equals 7. These would be my restricted values for this problem with the plus 28 switched to a minus 28. So x cannot be here, -4 or 7. Something that we might kind of notice is -4 and 7 are just the opposite signs of the m and n that we find here. Importantly, when we have the a equals 1 situation. I think it can be easy to fall into the trap of finding your m and n, getting +4 and -7, and then writing those as the answers. We want to be careful, though. It's always a good idea to just go through these couple of steps, make sure everything is correct, right? It's easy to kind of recognize this pattern, but to just get it a little bit wrong and then end up with the answers that you're giving are the negatives of what they ought to be. So the +4 is what comes into the factorization, but then it needs to get kind of moved to the other side in the equation solving steps to become a -4. So, when you start recognizing these patterns, sometimes there are patterns that it's good to recognize and that can be good shortcuts. This is one that I think, anytime that you're dealing with sign changes, it's a really error prone bit of math. I would be extra careful. So I would always go through and write out the details. It's only a couple more lines, just so that you're careful and get the correct signs on everything. Okay, so now let's look at simplifying rational expressions. And give me just 1 second here. Sorry, I'm trying not to blow my nose right into your microphone. So, simplifying rational expressions. Well, we know that kind of fundamentally a rational expression is a fraction. So let's start with the simplest fractions. I mean, fractions aren't all that simple to begin with, but let's start with the simplest ones, just with numbers. We have fractions like 1/2 or 2/3 or something like that. But we also have fractions like, say, 6/8 or 7/14 or 12/3. We have fractions like that as well. What's the difference between these? Well, these ones are simplified. These ones are not. Why are the ones on the right not simplified, but the ones on the left are? Well, because the ones on the right have a common factor that exists in the numerator and the denominator that we haven't divided out. So let's take, for instance, 6/8. Well, if we factor the numerator and denominator into their prime factorization, I factor 6 as much as I can, 2 times 3. I factor 8 as much as I can, 2 times 2 times 2. And I do notice that a factor of 2 can divide out, leaving me with 3/4. Why can that factor of 2 divide out? Well, kind of the intermediate step here is, well, I know that a over b times c over d equals a, get myself a little more room here, equals a times c over b times d. So fraction times fraction, when I'm multiplying, I multiply the numerators, multiply the denominators. Be very careful that doesn't hold in addition. But I can go left to right, but I can also go right to left. I can go the other way here as well. So 2 times 3 over 2 times 2 times 2, I could choose to make this 2 over 2. times 3 over 2 times 2. I could do that. There's nothing wrong with that. But a thing over itself, I know is just 1. So this is just 1. So 3 over 2 times 2, or 3 over 4. Okay. So when I have things multiply together like this in the numerator and denominator, I can divide out common factors. Now, very important, I cannot say something like 6/8 equals 2 plus 4 over 4 plus 4, and like divide out the 4s to get 2/4 or something. I cannot do this. I mean, I guess I could write 6 as 2 plus 4 and 8 as 4 plus 4, but I can't then divide out that 4 like that. So I don't want to get tempted to do something like that. The same would be true with 7 over 14. 14 is 7 times 2, and the 7's can divide out, leaving me with 1/2. So when I divide all of the stuff out of the numerator, that leaves me with a 1 in the numerator. And a 12/3, 12 is 4 times 3. I could divide out the 3's, and this just leaves me with the whole number 4. When I have a 1 in the denominator that's left over, that's all that's left over in the denominator, it just essentially goes away. So just remember these special cases. But if it kind of like I said, if these really are the simplest rational expressions, do we think the procedure, the general idea, is going to change when I get to something more complicated? Well, no, the general idea won't change. If I have a rational expression that's like x plus 1 over x plus 3 times x plus 1, I see that I have a factor of x plus 1 in the numerator and denominator that can divide out, and I'm left with 1 over x plus 3. The same idea applies. So let's look at a few specific examples down here. So we'll start by simplifying a somewhat simple rational expression, a linear over a linear. 5x plus 5 over 6x plus 6. And again, remember, what I can divide out is common factors. Something that's multiplied against everything else in the numerator and something that's multiplied against everything else in the denominator. Well, so that kind of gives me a clue that I want to start by factoring the numerator and denominator, right? The same way that I did up here with 6 and 8, factoring them to their component parts, their prime number parts. Well, here I want to factor out greatest common factors and so on. I noticed that with 5x plus 5, there's a greatest common factor of 5, leaving me with x plus 1. And 6x plus 6 has a greatest common factor of 6, leaving me also with x plus 1. And now I do notice a common factor in the numerator and denominator, specifically this x plus 1. So this leaves me with 5/6. Now, something that I want to recognize is that this is an expression with x's in it. It kind of implicitly has this idea that I can plug different numbers into it. I could plug in, x equals 1 or x equals 10 or something like that and get an output. My argument here is that no matter what I plug in, I get 5/6 out. If I plug in x equals 1, I get 5 times 1 plus 5 is 10. 6 times 1 plus 6 is 12. 10/12. Well, that does simplify to 5/6. I should probably be careful, though, because I can't plug in every x. I can plug in most x's. But I probably ought to make note of the restricted value. 6x plus 6 equals 0. or x equals -1. Maybe I won't box that. I'll just put it in a bubble down here. This is finding our restricted values. And then I'll say x cannot be -1. So these are equal. This is equal to this, number 5/6, so long as x is not equal to -1. The left-hand side and the right-hand side are equal for all values of x that you could input, x equals 1 or x equals 10 or something. The left side will always simplify to just 5/6. But if I try to plug in x equals -1, the left side kind of blows up. It's undefined. But of course, 5/6 is not undefined. Those two sides would not be equal when x is not equal to -1. So I just have to be careful, make sure to always recognize my restricted values. And I would recommend just always writing them explicitly as a reminder. These two sides, this left-hand side and the right-hand side, are only equal when x is not equal to -1. Okay, let's do the same thing down here. Again, I have a rational expression, but now I have a ratio of two quadratics. So a little more complicated than a ratio of two linears. X squared minus x minus 12 all over x squared minus 8x plus 16. Let me start by factoring. I'll factor the numerator and factor the denominator. Well, minus 12, I'm looking for two numbers that multiply to minus 12 that add to -1. I think that's -4 and +3. If I multiply that up, my first give me x squared, outside's +3x, inside's -4x, so that does give me a net minus x. And then -4 times 3 is -12, so that looks good. And then x squared minus 8x plus 16, this seems like it might be a perfect square polynomial, perfect square quadratic, because my first and third terms, my quadratic and my constant terms, are perfect squares. So x squared is just x squared, and 16 is 4 squared. So is my middle term plus or minus 2ab, or 2 times x times 4? Yeah, it's minus 2ab. So I think this is going to be x minus 4 squared. If I imagine x minus 4 times x minus 4, my first would give me x squared. My outsides and insides would give me minus 8x. And my last would give me plus 16. Looks good. I notice I can simplify. One of the x minus 4s on the top divides out one of the x minus 4s on the bottom, leaving us with a single x minus 4 in the bottom. And we see that this quadratic over quadratic simplifies down to x plus 3 over x minus 4. Now, if we really wanted to be technical here, x equals 4 is the only restricted value on the left side, and it's still a restricted value on the right side. And so I guess we don't maybe have to write the restricted value out, but it's usually good practice to do so. So let's find our restricted values. And when I go through these rational expression problems, sometimes I'm using similar work from in one step versus another, so I can reuse the fact that I already know how to factor this denominator. I figured that out in order to simplify. So I know my only restricted value is x equals 4. So I'll just write over here, x cannot be 4. Like I said, I mean, it's still implied by this right-hand side. So maybe technically we don't need it, but it's good practice to just write all of your restricted values. Okay, and then let's look at this example. We have a cubic over a cubic, actually. Well, what are my restricted values first? Well, I think I'm only going to have x equals -1. I see that x equals -1 is going to be a restricted value, and maybe we'll argue in a minute why it's going to be the only one. These are a little bit more difficult to factor. So let me actually come off to the side over here and do some scratch work to factor these. So let's start with the numerator, x cubed plus x squared plus x plus 1. I want to factor this. I don't really know how to factor cubics very well, unless there's some difference of two cubes, which this is not. But I do know that one method I can sometimes use is factoring by grouping. I can look at my first two terms and my last two terms. I do see a common factor of x squared, leave me with x plus 1. And then nicely enough, x plus 1 is just 1 times x plus 1. And now factoring out the common factor of x plus 1, I get x plus 1 times x squared plus 1. So that is my numerator. Note that x squared plus 1 cannot factor any further. I would be looking for two numbers that multiply to make positive 1, the constant term, but that add to make 0 because I have an x squared plus 0x plus 1. There's no two numbers that multiply to make positive 1 and add to 0, so this can't factor any further. All right, and then my denominator, x cubed plus 1. Well, wait, that's a sum of two cubes. That's one of my special products. I know that x plus 1 factors out of there. Let's kind of revisit the special product really quickly as kind of an aside. When we covered special products, we hadn't yet covered quadratic equations and the zero product property. So we basically just said we kind of memorized that for the sum of two cubes, the sum of the bases factors out, and for the difference of the two cubes, the difference of the bases factors out. But is there maybe a deeper understanding here? Something that we can understand more deeply that means we don't have to memorize so much? Maybe there is. What if I had an equation instead of an expression? X cubed plus 1 equals 0. Or if I had x cubed minus 1 equals 0. Do I know a solution to either of these equations just by guessing? Well, sure, I know that x equals minus 1 is a solution, or x equals plus 1 is a solution to this one. But I also know that if a number is a solution, let me go up a little further. Go up to this one. If a number is a solution, like if -6 is a solution, that's related to x plus 6 equals 0. I should see a factor of x plus 6. That should be a factor of my quadratic equation, or my quadratic expression. So if I can identify a solution of a quadratic equation, that gives me a factor of the quadratic expression if I put everything on the one side. And that's through the zero product property. Give me 1 second. Okay, so if I can identify an equation or a solution to a quadratic equation, that gives me a factor of the quadratic expression. Now, this isn't a quadratic, but it's a cubic, and it seems like it should work pretty similar qualitatively. If I identify a solution of the cubic equation, that seems like it would suggest that that should give me a factor of the cubic expression. So x equals -1 is a solution of the equation, or in other words, x plus 1 equals 0 is what leads to x equals -1. So I think that x plus 1 should be a factor of x cubed plus 1. Right? X cubed plus 1 should equal x plus 1 times stuff, so that when we have x cubed plus 1 equals 0, that would factor to x plus 1 times stuff equals 0, and we would get our x plus 1 equals 0 from the zero product property. And similarly, x equals plus 1 is a solution. Therefore, x minus 1 equals 0 is what we should get out of the zero product property, meaning that x minus 1 should be a factor of x cubed minus 1. So we can actually use this fact that I know solutions to these two specific cubic equations just by guessing the solutions, and that gives me the factor. So that's just kind of an aside. But x cubed plus 1, I know that x plus 1 factors out. I know I need an x squared, so that x times x squared is x cubed. And I know I need a plus 1, so that 1 times 1 equals 1. But again, I have a problem here. If I just leave it like this, then I have two cross terms. I have a plus 1x squared and plus x. These are the cross terms that show up as a result of this factorization, the multiplication of these two factors, but don't show up in x cubed plus 1. So I need to get rid of these. So if I do a minus x here, this will give me a minus x squared minus x, getting rid of all of this cross term nonsense that I don't want. So I see that x cubed plus 1 and the denominator has to be x plus 1 times x squared minus x plus 1. And now after all of this, I do see that I have a common factor in the numerator and the denominator, this x plus 1. So I can say this equals x squared plus 1 over x squared minus x plus 1. And again, that's under our restricted value, x not equal to -1. So you can see that working with rational expressions, I mean, we haven't really introduced many new ideas, maybe the idea of a restricted value. Most of the challenge of working with rational expressions is, one, being really careful with your fraction rules, making sure to use the proper fraction rules and identities and properties. And two, understanding factoring and quadratics and so on, and how quadratic equations work and how to factor quadratics. So we're really building on really what we've done all semester long. And of course, with quadratic equations and so on, there's a component of solving linear equations. So we touch on that as well. Okay, so for the rest of the class, we're going to just work through a few problems on the worksheet. For these three problems, let's take about 6 minutes for these three problems, and then we'll come back and discuss. The goal is to simplify, so we want to factor the numerator, factor the denominator, divide out anything we can divide out, and then also make note of our restricted values. We would like to do that for each of these three problems. So take about 6 minutes to do that, we'll come back and discuss. Okay, it is a little under 6 minutes, but let's discuss these three. I finished them up on the screen here. The first one, pretty straightforward. we have a linear over a linear. So really the only thing we can reasonably do is factor out a greatest common factor. And we see that an 8 factors out of the numerator and a 3 out of the denominator, leaving us with a common factor of x minus 12 that can divide out. When we divide that out, we get 8/3. And we note our restricted value is when 3x minus 36 equals 0, or when x equals 12. So this left-hand side equals the right-hand side 8/3, but only when x not equal 12. So we want to make sure to include that restricted value in there as well. For the second problem, we have quadratic over quadratic, so we want to factor both of these first. X squared plus 4x minus 5 factors into x plus 5 times x minus 1. This is one where we could probably either just do guess and check, or if you want the more structured approach, you can definitely do the M and N, looking for two numbers that multiply to -5 that add to +4. And write out all of your list and see which one works. But we get x plus 5 times x minus 1. The denominator we might recognize as a perfect square, x squared minus 2x plus 1. And this factors into x minus 1 squared. So x minus 1 times x minus 1. We see that our factor of x minus 1 in the numerator cancels with or divides out one of the factors of x minus 1 in the denominator, but leaves one of those factors in the denominator as well. So we end up with x plus 5 over x minus 1. And we see from the factorization of the denominator that the only restricted value is x equals 1. That's the only number we can't plug in, or the only number for which the denominator equals 0. So therefore, we just say x not equal to 1 over here to indicate that restricted value. And then last, our third problem, x squared minus 4 over x squared plus 6x minus 16. I note that this numerator is a difference of two squares. So it's x squared minus 2 squared. It factors into x minus 2 times x plus 2. The denominator, I'm looking for two numbers that multiply to -16 and add to 6. I think this is going to be plus 8 and minus 2. So this denominator factors into x plus 8 times x minus 2. And we see we have a common factor of x minus 2 in the numerator and denominator. Dividing those out gives me x plus 2 over x plus 8 that's left over. And again, my restricted values, I look at the factorization of my denominator, setting it equal to 0, I can see that my restricted values are x equals -8 and x equals 2. Plugging in either of those will give me a 0 in the denominator. So again, I note those over here, that x cannot be equal to 2 or -8. The restricted value of -8 is still apparent on the right-hand side, x plus 2 over x plus 8. But we actually lose the x not equal to 2 restricted value when we simplify. So we want to, we really need to make sure that we state that explicitly. The left side is not equal to the right side at x equals 2, because the left side is undefined at x equals 2, and the right side is going to be what? 2 plus 2 is 4 over 2 plus 8 is 10, so 0.4. Those two things aren't equal when x equals 2. The left side's undefined, the right side has no problem, so we need to make sure to indicate that we're imposing a restriction that x is not 2. Okay, and then these last two problems, we'll work through these, maybe take about 3 minutes. That might be a little aggressive for the time, but we'll try to get them done in 3 minutes, 3 or 4 minutes, just to work within our time constraints here. We have about 7 minutes left. So take 3.5 minutes for these two, and then we'll discuss them. Okay, in the last couple minutes of class, let's discuss these two examples. So the first one is a cubic over a quadratic. So we know to factor a cubic, we don't have a whole lot of options. It's not a difference or sum of two cubes, but we can factor this one by grouping. We can look at the cubic and quadratic terms. We can factor an x squared out of those, leaving us with x plus 3. And it turns out that the last two terms, 4x plus 12, we can factor a 4 out. And that also leaves us with an x plus 3. So this one worked out just right to where we can factor by grouping. This x plus 3 factors out, and we're left with x squared plus 4. So my numerator is x plus 3 times x squared plus 4. My denominator, x squared plus x minus 6. I can use guess and check here. One kind of test-taking strategy is, well, if you're given a rational expression problem and told to simplify it, I mean, it could already be in simplest form. That's possible. But probably, most likely, there's going to be a factor that divides out if you're asked, the problem on an exam or something. And so we might think to ourselves, well, I mean, x squared plus 4 isn't likely to be a factor of something that's only a quadratic. So is x plus 3 a factor? That gives us a pretty decent clue as to where we might go, right? And we do see that x squared plus x minus 6 is x plus 3 times x minus 2. The x plus 3's divide out, and I'm left with x squared plus 4 over x minus 2 as my simplified form. But again, importantly, I want to note my restricted values when the denominator is 0, or whenever this product is 0. I want to get my product before I divided anything out. So x minus 2 times x plus 3 equals 0, or that's when x is 2 or negative 3. So my restricted values are 2 and negative 3. I don't want to plug either of those in. Again, the x equals 2 restricted value is still obvious, but we lost the obviousness of the x equals negative 3 restricted value. And then for this example down here, x to the 4th minus 1 is a difference of two squares. It's x squared squared minus 1 squared. This factors into x squared minus 1 times x squared plus 1. And I actually notice I could factor this further, but I actually notice my denominator of x squared minus 1 right here. So I'm not going to go any further. X squared minus 1 times x squared plus 1 over x squared minus 1. The x squared minus 1's divide out, and I'm left with simply x squared plus 1, just a polynomial. So I suppose a polynomial is even kind of a rational expression just with a denominator of 1. But it's not a very interesting rational expression. It's simplified down quite a bit to just a polynomial. And again, I want to look at my denominator, x squared minus 1. I can set that equal to 0, factor, and see that my restricted values are x equals plus or minus 1. So I just want to make a note that x cannot be plus or minus 1. Of course, naturally, plus or minus 1 can get plugged into x squared plus 1 with no problem. But because this came from this guy and we're saying that these two are equal, we have to restrict those numbers. Okay, so that finishes us up for today.